Right, so now let's look at the part 3 of today's class where we're going to introduce the second major data type that falls into the category of linear data structure. So it's called a queue, as opposed to the stack where because you are reading and also you are removing element from exactly the same location, which is the top of the stack. You have this last in first out principle. Queue is actually in the opposite, right? So just like a real life queue, you will have the head of the queue where the customer is being served and customer will be removed from the queue. But when new customer join the queue, they will be join the queue at the tail of the queue. Because of that, the queue have this nice structure of first in, first out. This is the kind of principle that I think most of the customer want, right? Or first come, first serve. So in terms of operation, we name it slightly differently. Joining the queue, we call it in queue. Leaving the queue, we call it dequeue. And pick is still the same. It try to look at the value without looking at the head value without doing any modification. So in terms of terminology, it's not top and bottom anymore. We have the front of the queue where the dequeue will happen. We have the back of the queue where the in queue will happen. So a lot of real world situation, majority of the service queue are where the queue concept is being utilized. But even in the computer application, right? I mean, if you try to compete for printer during the busy period, you will discover that really you will have this common pool of almost like a job queue where hopefully you hope that is a first come first serve. The job is being inserted into this pool, and then depending on the arrival time, the job will be processed in sequence. So that essentially is a queue that is designed and designated for the printer scheduling. And of course, I mean, if you send the data, that's also basically a kind of the queue. Okay, so again, we try to define the data structure at the abstract level first. Then before we go into the actual implementation, we will go over the operation one by one. The first one will be the in-queue operation, essentially inserting a new piece of data into the queue, right? So again, we mentioned one of the major difference between queue and the stack is that when we insert a new piece of information, data element, it has to occur at the back of the queue or the tail of the queue. This is one example. Again, also we present this vertically, but yeah, we have both the head and tail, and the data will actually, new data will appear at the tail, not at the top anymore, right? So we have head and tail. And then when we pick the head element, the element that's about to be dequeued next, right? So in this case, you see that the top element, the head element will be grape, right? It will be returned. Finally, the dequeue operation, you simply remove the head element, right? So in this case, the top element, which is grape, will be removed, and the second second item that's in line will become the new head, right? Well, the tail pretty much stay the same. So how do we use it? Queues, of course, if you use it, is a very straightforward usage case. But now, in this particular example, we try to use the recognition of palindrome as one example where we can simultaneously use both the queue and the stack, right? By utilizing their unique property. So palindrome is a special type of words that's essentially reading or spelling in the same way, whether or not you start from left to right or right to left, right? The couple example words over here, Matin, refer, radar, they are all following this particular principle. You can spell from the left hand side, you can spell from the right hand side. They all look the same. So how do we detect palindrome? Okay, so this is one idea. Again, definitely not the only one idea. I mean, you can use iteration, you can use recursion, whatever. A lot of ways where you can do it. But since we are introducing data structure, so we're going to use both the stack and queue we have just introduced to do this check. So basic idea is as follow, right? Because a stack basically is last in first out, but the queue is first in first out, right? So if you like push and queue the element into the stack and queue respectively, and then you begin to remove element one at a time from stack and queue, because for stack is last in first out, you get to see the last element first and progress into the beginning of the words. While for the queue is first in first out, so your first element uh, inserted into the queue will also be dequeued the first. So essentially, when you are comparing the element that come out of stack and queue, you are comparing the first element, which is from the queue, to the last element, which is from the stack, right? You are comparing, you are essentially almost like you are checking one from the tail of the end of the word, and on the right hand side, you are checking from the beginning of the word, right? So if you check that they are equal at all the position, then basically it means that this particular word satisfies the palindrome property, which is like you spell from the beginning, you spell from the end, the word will be exactly the same. All right, so this is a very simple implementation that we see. We create two data structures, stack and queue. The first thing that we do is that we insert the information, insert each and every character from the word into the stack and also into the queue. It's just a method that we use will be different. One is push, the other is called in queue, right? And then after that, what we do is that we're going to remove element one by one. One is from the stack. We use the pop operation. And then from the right hand side, this is the queue. We remove the element from the queue. Then we compare. If the left doesn't equal right at any given point, immediately we say that the failure is detected. We'll return false. Otherwise, we'll return true. Okay, so we have talked about the abstract definition of the data type. Now we are ready to think about like how can we implement that in Python. Again, using the only like well-known containers data structure that's known to us at the moment, which is list, right? So we'll try to, again, just like before, try to use list to implement this concept of queue. For the in queue operation, what we do is that we're going to append item one by one, right? So this is based on the assumption that the first element is the head of the queue, while the last element will be the tail of the queue, right? So append operation is actually perfect for the this in queue operation, right? Because if you look at it, when we are in queuing elements, the new element just simply got inserted at the end of the list. You don't need to do any modification to the existing element. So this is unlike the previous implementation that we had for the stack, right? In the previous implementation, we actually have to shift the data every time that we have a new element being pushed in. But in this case, during the in-queue process, nothing need to be done, right? So in terms of complexity, again, it doesn't matter how many elements that you already have inside your list, your in-queue operation is always constant time, right? Just do an append. The pick, just like before, you just read the value and then return, right? So because of that, complexity will also be constant time. You just read the element that's at the index 0. Finally, for the dequeue operation, this is very similar from the pop operation, right? So number one thing that we do is that we check whether or not the content is non-empty. If it is non-empty, we're going to get the value of the first element and then we delete it. So again, in terms of complexity analysis, you'll see that because the more element that you have, the more shifting of the element will need to occur. So because of that, your complexity will be linear in the numbers of elements. The more element that you have, the more shifting work you have to conduct, right? So that will be in linear time. All right, so once we have the queue, right? Queue is relatively straightforward. We can use that to generate a lot of variants. And one of the variants is called priority queue. Very important uh, data type. Turned out to be in a lot of settings even more useful than a regular queue. So in the regular queue, what we have is actually first in, first out. Your arrival time to the queue determine your service order, right? So that's why you have first in, first out property. But priority queue comes with a special property called the priority, right? So every element will have a priority attached to it. The next element that get to be dequeued will be dependent on the priority. The higher priority item, even it has like just recently arrived, might potentially be handled earlier than the very first element that's been inserted. Okay, so in terms of operation, exactly the same. You still do in queue, you still do dequeue, you still do pick, right? It's just that the outcome of those particular operation depends on the priority, not the arrival time. All right. So a lot of example, of course. You can use priority queue to rank your to-do list. You can at a hospital, you can rank how you're going to what should be the order that you're going to see the patients, particularly during the emergency room. In the ER department, definitely you're not going to see the patient based on their arrival time. You see the patients after you have walked them through the triage process. You determine their priority, then immediately for those high priority patients, you have to see them immediately, right? And also even on your computer, you just open up your task manager, right? So you will see the depending on the urgency of the task, the more urgent task will definitely receive higher priority value. Okay, so this is at an abstract level. How do we define those operations? And this is one example. Over here, we just simply assume that the priority depends on the alphabetical order, right? This is just for simplicity. In general, it can be based on anything, right? But over here, it's just a alphabetical order. So initially, the content of the PQ, priority queue, is a grape followed by orange. Now we have a new information, which is kiwi, has been inserted. Supposedly, I mean, in the normal queue, it should appear at the tail. But now, because this priority queue is based on alphabetical order, so you can see that kiwi, once inserted, it actually jumped to the second place. When it comes to picking, so again, you try to look at which particular element is at the head. That will be the element that with the highest priority. Finally, the DQ, right? So it happens again at the head, just like before. But instead of, again, removing the earliest arrive item, you remove the item with the highest priority. In this case, that will be the word that was the highest alphabetical order. Okay, so now we have all the necessary information. We can begin to think about how do we implement priority queue based on the list. We will like to, again, multiple ways where we can do the implementation. Here are just some ideas. We can use the in-queue operation. So if we use the in-queue operation, essentially, we are placing the element in the, we can place the element in the last position in the array, right? So this can be one potential way of doing this. And then you can see that if we just do that, this is like a pen, right? Pretty much the same as the regular queue, right? So your complexity will be constant time, O1, right? If you do the picking, right? So again, you need to return the minimum data element in the array. What should be the complexity then? Right, so I think this again is not something that's very straightforward. I have to think about carefully what that is. If you try to implement that in a very straightforward manner, right, which means that whenever you have the pick operation, then you walk through like each and every element. Let's say you have like one until like in total n different element, right? And then your in queue doesn't really maintain any specific order because the element is always inserted at the as the last element, right? So your in-queue operation as a result, although it saves time, but it doesn't really at that time doesn't really allow you to construct a list of items that follow specific order, right? So your pick as a result, if you just do it in a very naive manner, you're going to look through each and every element. So your complexity potentially will be O(n), right? And DQ, it is actually also the same. You identify the minimum data element. For that, you're going to take you n time, and then you're going to remove that. After you remove that, in the worst case, you're going to incur another n shifting effort, right? So again, in total, in the worst case, it will still be linear time. Okay, so the question over here is that can we do better, right? So if you look at in queue, you're already constant time, so I mean, not much you can do. For pick, right? This is the place where potentially you can do better, right? So I mean, again, for DQ, if you look at it, because it really involves, no matter how efficient you are in identifying the minimum data element, you will still need to shift the element that's inside an array after deletion, right? So that part cannot be avoided, right? Complexity in the worst case will still be O(n). But picking operation doesn't need to take linear time every time. And the reason for that is because during the in-queue process, every time a new element comes in, you can imagine that you can use a minimum variable to keep track of the current minimum. Every time you see a new element coming in, I say this element is x, you can compare this x to the min. And if your minimum is greater than x, then what you do is that you will replace your minimum with the x value, right? So you will know actually, I mean, because all the element that you ever are going to see inside a priority queue is actually inserted using the in-queue method. This basically means that your pick operation will actually doesn't need to actually do a comprehensive search. You can simply rely on the information that you've seen earlier to immediately return the minimum data, which is this value, that this particular variable over here, right? And of course, I mean, during the DQ process, you have to remove that minimum data, right? So what you will do is that you're going to look for the second minimum data, the second smallest element. That will be the new element, a new minimum, right? So I mean, this particular DQ process, as you are removing the element, make sure that, I mean, since you are shifting the data anyway, right? So during the shifting process, identify the new minimum, right? So this need to be updated. So the purpose is that so later, if you need to do the pick, you can improve your performance, right? So instead of linear time, you can really do it in constant time. All right, so the second idea over here is to maintain the list in a sorted order, right? So if you maintain a list in the sorted order, basically means that, for example, if you like use value to represent the priority, right? Let's say the larger the better, right? So you can have for example from 1, again the top the lowest priority all the way until n, right? So this is how you store the data. So during the picking process, of course, if your list is already sorted, you can identify the minimum data element immediately, the data with the most priority almost immediately, it will be O(n). And if you have DQ, right? So what it basically means that, again, you want to find the minimum data and you want to delete it immediately. Over here, if our priority depends on the value of the data element, then again, to save time during the DQ, it basically means that you should actually sort your array, sort your list in the descending order, right? So you start from the largest value all the way until the smallest value. In this way, right, when you need to do any DQ, you don't need to do any data shifting, just remove the last element. That will be it. And then you know that the next item that's down the priority list will be the last remaining item, right? So everything is in place. You don't need to do anything. So in terms of complexity, DQ is also O(n). But the real effort happens when you need to do an in-queue, right? When you have a new element that come in the worst case, again, if this element happen to be the largest, let's say right now the largest element is n, right? So in the worst case, you can have, let's say, n+1, which means that you have to go through each and every element until you identify the right place and you do the insertion, right? So this is actually very similar to the move left operation that you will see in the insertion sort, right? So that particular step will be linear time. Okay, so this is the trade-off you pay. Your pick operation is very efficient. DQ also very efficient, but in queue you have to spend a bit more time, in linear time to be exact. The final idea is actually to use a binary search tree. Again, over here, we haven't really introduced the tree structure. This is the next lesson, but we are jumping ahead a little bit, right? We try to see how we can actually use this particular structure to make it more efficient, right? It turns out, again, although the worst case scenario, you still have ON, which is not very ideal, ON also over here, but on average, by using the binary search tree, if you are really careful, you just use some specific technique, you can improve on average your in-queue time and DQ time to log n. And we know that log n is extremely efficient. If even for very large n, if you observe it, it doesn't even grow. You cannot even notice the growth, right, of the execution time, right? So in practice, this is very efficient, but also, I mean, in the worst case, it can still be bad. But it's just that those worst case doesn't really happen very often. And this is one example, right? So you'll see, you'll probably appreciate it more next week when we have a proper introduction of the binary search tree. Finally, this is the comparison between different kind of priority queue. You have unsorted list, in which case your in queue is fast, your peak can be fast as well, but your DQ will be slow. Or you keep it as a sorted list, then you have like n11, and then if you have a binary search tree, in the worst case, still n for both in queue and DQ, but on average, which is the practical case, most of the practical use case, you have log n and log n. So the question over here is that, yeah, seems to be like a difficult choice, right? Because sometimes this is better, sometimes some operation, this particular method is better. On average, this seems to be better than both, right? So which implementation is better, right? So I guess the answer really depends on in terms of our own use case, do we in-queue information more and then DQ information more, right? If you, or do you actually need to look at the information more? And once you have inserted the information into the priority queue, you don't really change it anymore, right? So if that is the case, maybe unsorted list is actually good for you because in queue is actually very fast. Peak is also very fast. It's just that when you want to remove the information, this may be time consuming, right? If it is actually the other way around, right? So you in queue, I mean, you rarely do the in queue, but you do the picking a lot, right? So in that case, maybe sorted list will benefit you a little bit, right? So again, over here, if you do in queue, DQ equally frequently, then maybe this binary search tree based approach will be more beneficial because for both operation, you actually get log n, right? So again, there's no one clear answer for it. Sometimes this is better, sometimes this is better, right? It all depends on the kind of use case that you have in mind. So as a final slide to summarize, we introduced 3 different types today. Strictly speaking, 2 different categories, but 3 different data type. The first is last in, first out. This is the stack. In terms of operation, we have the push, we have the pop. And then we have the queue data structure, which give you this property of first in, first out, right? And then the operation name is called the in queue and DQ. Finally, we have priority queue, right? Priority queue also have in queue and DQ, but the order in which item get processed depends on priority. It's not arrival time anymore. So we still have a couple more in-class exercises, right? So think about that. how you can solve it. This is the queue, simple exercise on the queue operations. And then we have some additional slightly more involved cases, right? So the first one is try to simulate a queue, but assuming that you do not have queue, but instead you have two stacks. Try to think about how do you implement we have this dequeue operation, right? So use this as the reference. Try to imagine if you want to implement the in-queue operation, how do you do it, right? And then you analyze what should be the complexity for in-queue, what should be the complexity for dequeue, right? So every operation, just assume that it will be O1, constant time, right? So then think about how can you do the proper implementation. Okay, so as a final takeaway, if you are interested in learning more about the list operation efficiency, you can actually just check out this page. This is the official information that tell you if you do any of the list operation, how long does it take in terms of complexity. So this is where we are. We have just finished the first data structure content. The following weeks, we will have binary tree, and after the break, we will have the most comprehensive and most complicated data structure in this whole class. Is called the graph. We will spend 2 weeks on that, right? But for now, let's stop it here.